All right, in this lesson we are going to look at a topic called cross sections of solids. So this is another way of using integration to find the volumes of shapes or objects or three-dimensional figures. So what we want to do here is be able to find the volumes of three-dimensional figures, and in these kinds of questions we're given some information about the shape of the base, and we usually need to figure out, or we're given some information about what a cross section or a slice through these objects looks like. And then we want to sort of integrate to sort of add up all of these cross sections and in that way find the total area of this figure. So in problems of this type, we're using basically a slicing method. We're taking our figure here and we're dividing it into infinitesimally thin slices along one axis. So we're given a description of the cross section of the solid, or what the shape of what each of these little slices looks like, and some information about the base. And then we integrate from one side of the solid to the other to find the sum of the areas of all of these cross sections. And by adding up the areas of all of these cross sections, we get the total volume of our shape or our figure. So we're going to look at an example here, and I'm calling this example 0 because this is not sort of the typical example that you're going to see for this kind of problem, or the kind of problem that you'll be asked to solve, but I think it kind of helps to illustrate what the method that we're going to be using kind of works like. So we've got a cone here, which I have drawn in such a way that it is a half cone, I guess, and I've sort of placed it so that one half of it lies along, the middle of the cone lies along the x-axis. This is our z-axis. Up here is the height, and our y-axis would kind of go sort of perpendicular to this. So this line along the base there is along our y-axis. So our y-axis would kind of go like this, and that would be positive y, like that. And we want to find the volume of this cone. And we're told some dimensions of it. The height is 6, so that's sort of 6 along here from the origin to this point right here, and the base has a radius of 3, so that's sort of that radius right in there. Now, we already know the answer to this question. We know the formula for the volume of the cone, or if we don't, we can quickly look that up. We know that the volume of a cone is 1/3 pi r squared h. So if we sub in the information that we have, those dimensions 3 and 6, our volume here is for our half cone. So let's say the volume that we want here is going to be 1/2 of this 1/3 pi r h. We know our radius here is 3, so 3 squared, and our height is 6. So we can plug all that stuff in, and we get an answer of 9 pi. Now, the point here isn't just to get that answer of 9 pi, it's to use this cross-section integration method in order to get, and see if we get the same answer, 9 pi again. So how do we do this using this this new method? Okay, so first of all, we have to think about what if we were to slice this into cross sections, and these cross sections are going to be like perpendicular to that xy plane that is forming the base of our half cone here. What are our cross sections going to look like? And they're going to be the same as this semicircular base. So a thin cross section might come like this, up like this, and come down over here like that. Okay, so it's going to have some radius here, r, in the middle, like that, and it's going to come across kind of like that. So that's the first thing. Our cross section is a semicircle, and it is has got a radius r. Oh, that's not how you spell circle. Let's fix that. It's got a radius of r equals, well, we don't know what r is yet, so we'll just leave it as r. And it's perpendicular to the x-axis. Okay, now we want to come up with an expression for the area of that cross section. Okay, so we know that the area is going to be 1/2 and then pi r squared because it's a half circle. Now, how do we figure out what that r is? We want it in terms of a variable that we can use in our integration. So the obvious variable here is going to be x, because we're going to imagine, like, when we do our integration, we're going to start down here at 0, and we're going to go over here to the end of this cone here where x is going to be equal to 6. And so you can kind of imagine, as we start here, our cross sections are extremely small, but as we move along, as x increases, we can, like, envision these other cross sections, which are semicircles here. They're going to get larger and larger and larger, okay, until finally, when we get to our base here, they have a radius of 3. So we need an expression here for this radius in terms of the information that we have. And to get this expression, we're going to have to use similar triangles. So we have one triangle that is formed, if I can just sort of outline it, right here, here, and here. And then let's make that line a little bit nicer there. No, we'll just leave it like that. You know what I mean. And our other triangle comes along here and then comes down here, and forming that radius of that little cross section in there. So looking at that special triangle, that triangle, we know that these two triangles are similar to each other because they share angles. They both have a right angle in here, and they share an angle down here. So that means the lengths of their sides are proportional. So that side in the small little triangle, r, over, well, this distance from here to here in that small triangle is x. So r over x is going to be equal to, in our big triangle, we've got a height of 3 here, and that long side is going to be, has a total of 6. So r equals 3 over 6x, or if we want an expression for r in terms of x, r is going to equal 1/2 x. We can take this and we can sub it into our expression for the area. So our area is going to be 1/2 pi. Instead of r, we're going to have 1/2 x, and that whole thing is going to be squared. And then we can simplify this a little bit to get 1/2 pi, I guess 1/4 x squared, and then I guess 1/8 pi x squared. Okay, so we have this expression here for the area of each one of our cross sections, and as we start from the origin and move to the right, the area of those cross sections gets bigger as x gets bigger. So how do we calculate our volume here? Well, for our volume, we're going to start at one edge of our cone, okay, at the very tip, so at x equals 0, and we're going to go to the other edge, to that base, that semicircular base, where x is equal to 6, and we're going to use integration to add up all of these areas. So we're going to add up the areas of all of our cross sections. So our cross sections are each 1/8 pi x squared, and we want to integrate with respect to x. So you've done a bunch of integrals like this before. We can basically pull out all of those constants. So 1/8 pi. If we integrate x squared, we're going to get x cubed 1/3, and we want to evaluate this from 0 to 6. Now at 0, at x equals 0, that whole thing is just going to be 0. So we're going to have, let's see, 1/24 pi 6 cubed, which when we work it out, 6 cubed divided by 24 gives us 9. So our answer here is 9 pi, just like we expected from the formula. Okay. So that's kind of an overview of the method. All right, we want to figure out an expression for the area of our cross section, and then we want to integrate over one end of our shape to the other to get our total volume. So let's take a look at another example here of a question that is more like the one that kind of question you might be asked. So find the volume of the solid whose base is enclosed by y equals sine 2x and x equals 0 from 0 to 2 pi, and whose cross sections are squares perpendicular to the x-axis. So it's probably a good idea to draw a quick little sketch of what this thing actually looks like here in the given information. So if we just draw the base here in the xy plane, this is our x, this is our y, they give us that y is equal to sine 2x. So that's going to look something like this. Just going to be a regular sine function. And it only goes as far as pi over 2, because at pi over 2, sine 2x is equal to sine pi, which is just back to 0 again. So this is our function sine 2x, which sort of encloses our base. And so it's enclosed by this line and, of course, this x-axis down at the bottom there. Okay, so this is the base of our solid here. And they give us some information about the cross sections. The cross sections are squares. So let's just come over here and draw a picture of our cross section. It is a square. Okay, and these squares are perpendicular to the x-axis. So if I imagine the z-axis sort of coming out like this, okay, our cross sections, we would have sort of one cross section that would be like the bottom of the cross section, and it would be a square coming up vertically out of the page here. So our square is going to have an area of, if I label each of the sides as b, the area there is just b squared. Okay, but this b, let me just change colors here really quickly. Like if this is the base of our cross section along here, it's sitting on this line right here, which is the base of our solid. So another expression for b there is that sine 2 theta, because as we move this cross section from one place to another, its height is going to change. These are different cross sections here, but the height there is always going to be from y equals 0 up to sine 2x, up to that curve sine 2x. So our expression here for the area, we can call it b squared or sine 2x squared. All right, so if that's the area of our cross section, to get our volume, we are going to integrate, and we're going to integrate all over the areas of all of these little cross sections. So we want to integrate sine 2x squared, okay, and we want to integrate from one side to another. So we're going to start over here where x is equal to 0, and we're going to end at the other end of our solid over here where this is pi over 2. And we're integrating with respect to x. Now, this is an integral that is hard to do analytically, so this is the kind of thing that you would just punch into your calculator if you had a graphing calculator and evaluate the integral numerically. So 0.785. Okay. So if you don't have a calculator to do the integration for you, the key thing to take away from this example is how you get the setup of the question. Okay, how you draw this picture to look at what your base is going to look like, how you get an expression for the area of the cross section, and again, our area of our cross section had to be expressed in terms of x here, and usually that's going to be sort of something in terms of this function that you have there, and then you integrate from one side to another to get your volume. All right, let's do an example where we can do the integration sort of analytically here. So let's see, we've got the base of a solid is bounded by the lines 1 minus x over 2, and it's called f at x, and g at x is negative 1 plus x over 2, and x equals 0. So I've already drawn a little graph here of what these lines look like. This first one here is f at x. Yeah, the red one here is f at x. And then the blue one down here is that line g at x. Okay. And of course, it's also bounded by, they say x equals 0. That's just telling us that we're only starting here at the y-axis. So that's x equals 0 right in here. Okay. So our base is this little triangle enclosed by these three lines here. Now, the cross sections, so we've got a nice picture of our base here. What about our cross sections? Well, our cross sections are perpendicular to the x-axis and are equilateral triangles. So our cross sections are going to look like this. This is an equilateral triangle here, okay? And so we can sort of say that each one of these are the same. Okay. Now, what we need is, and just sort of illustrate this, our base of our triangle would be along here like this. We can call this our base. On our diagram, that would be the line from here to here. Okay, or if I slid it, to the left or right, that base would get shorter or longer. Okay, this is like our base along there. Okay, so we need an expression here for the area of this this cross section here. Okay, well, we can start by getting an expression for this thing that we have called the length of the base. So the base of this triangle is going to be the distance from between our two functions here. So we can express this as just the value of f at x minus g at x. And we're given these two functions. So f at x is 1 minus x over 2. Sorry, not a pi, but x. 1 minus x over 2. And g at x is negative 1 plus x over 2. And I did it again. Let's try this again. Negative 1 plus x over 2. And so we can simplify this a little bit, and we're going to end up with, let's see, negative 1 minus negative 1 minus negative 1 is going to give us 2, and then negative x over 2 minus x over 2 is negative 2x over 2, so that's just going to be 2 minus x. Okay, so that's an expression for the width of our base. Okay, so our base here is 2 minus x. Now, what we need is an expression here for the area of this triangle, this equilateral triangle. So our area, we know, is 1/2 base times height. This is an equilateral triangle here. So we can maybe sort of divide this in half. We know that this angle down in here is 60 degrees. Okay, so we can use a special triangle here. If that's the base and that's height right in there, we could refer back to our 30, 60, 90 special triangle, right, which is 1, 2, root 3. This is 60 down in here. Okay, and we know that let's see, if we're looking for a relationship between the base and the height, let's see, and if these two, like this triangle, these are going to be similar triangles in here. So in our small little triangle over here, in our big triangle here, we want our height and we want b divided by 2, because that's this little bit right down in here. This is b divided by 2. Okay, that is going to be proportional. In our special triangle over here, our height is root 3 and our base there is 1. Okay, so we can take this and rearrange it. We have an expression here for the base, so we want height in terms of b here. So we can just take this and we can say, okay, h is going to equal root 3 over 1 times b over 2. Okay, so root 3 over 2 times b. So subbing that in over here, our area formula is 1/2 b times that expression for the height, root 3 over 2 times b, which is going to be root 3 over 4 b squared. Okay. Now we know what b is. B is just that expression we had for the base earlier. So this is going to be root 3 over 4 2 minus x all squared. So we've got an expression for our cross-sectional area in terms of x. So now we just want to integrate to find our volume. Our volume is going to be the integral of this expression here for the cross-sectional area, so root 3 over 4, 2 minus x squared. We're going to integrate with respect to x, and we can see from our diagram that we're going to start at a value of 0, and we're going to go to where these two lines intersect at x equals 2. So we want the integral from 0 to 2 of root 3 over 4 to minus x dx. Now let's evaluate this integral. Pull out the 3 over 4. If we're integrating, let's see this, we can get 2 minus x cubed. We're going to need a 1/3 in there. And I think we are going to need a negative sign out in front to cancel the negative sign on that negative x there. This is going to get evaluated from 0 to 2. So let's see what happens when we integrate this. Well, at x equals 2, this whole thing is just going to be 0. So we're going to get 0 minus, and then whatever we get when we sub in x equals 0. So that's going to be negative root 3 over 4, 1/3, 2 cubed. Okay. Those negative signs are going to cancel out, and let's see, we're going to get root 3 over 4, 1/3, 8. I can cancel the 8 and get like a 2, instead 8 and the 4 and get a 2. So it looks like our volume here is going to be 2 root 3 over 3. And we're done.